Okay, hello. Many of you have seen resampling methods, and even if you haven't seen it, I can convince you that you have in different forms. So that's why I won't spend a lot of time on it. So cross-validation is a way for us to calculate the test error, estimate the test error essentially. So resampling methods essentially are based on drawing samples from a training set and refitting a model. It's computationally expensive because fitting a model is computationally expensive. And then there are two main approaches. One is cross-validation to estimate the test error, and the other one is bootstrap. I won't spend time on bootstrap, I will focus on cross-validation. Cross-validation is used for mainly two purposes. Evaluate the model's performance, that's what we call model assessment. Sometimes we like to know what is the typical, what is the risk involved in each prediction? How much should we expect to be off? That's model assessment. Sometimes we use cross-validation to select a proper level of flexibility, meaning that when we have a family of models at our disposal, models that are indexed from simple to complex, how do we decide which level of complexity to use? Cross-validation can tell us. Cross-validation gives an estimate of the model's performance, and then we can select a flexibility that gives the lowest estimated or the best estimated model performance. Okay. So what is the test error? The test error is the average error in predicting the response to a measurement not used to train the model. Test error is in a way we want to know what's the risk. How much should we expect to be off? Now, we do not have access to the test error because the average error can only be calculated if we had infinite amount of unseen data. Infinite amount of data that was not used to train the model. Well, if we had any data, we would use it all to train the model, so there wouldn't be anything left. The test error, in principle, is unavailable to us, but we can estimate it. How? We hold out a subset of the training data from the fitting process and evaluate the model on the held out data. So we split the available set of observations into a training set and a validation set, which is also known as holdout set. Okay. So you shuffle the data, split it into two pieces, use one part for training, the other part for testing. The potential drawbacks is that splitting is random, so it will create a lot of variability, and only a subset of the data used to train. We only use this part to train. We don't use this part. So we have less data. The model's performance will obviously decrease because we have less data. In comparison, if we had used all the data, or almost all the data, we would have used more information, so the model would have been better. So the validation set error rate overestimates the test error in this case. That's a potential drawback. Here's an example. It's for a mean squared error, but as we can see that the validation error estimates with different degrees of the polynomial vary a lot. There's a lot of variability. Another approach is leave one out cross validation, where we leave one data point out and use the rest of the data to fit the model, and then we try it. And then we repeat it n times. Leave one out cross validation. It's the other extreme. If this is all the data, then this is all the data minus the ith observation, and then we use this data minus the ith observation to fit a model, and then we make a prediction, and then that will be yi hat minus I, meaning that this prediction at I did not use that data point, and then we subtract it from the true observation, squared sum it. That's for regression problems, but for classification we also do the same thing. We count the number of errors. Okay, so what's the problem with this approach? It's computationally infeasible because we have to fit the model n times, but I did a lot of work on this, and I received an NSF grant to support my work, and as part of that work we published a paper which essentially presents a scalable way of calculating this leave one out by approximating it. It was published last summer at the Journal of the Royal Statistical Society, Series B. Anyway, also published another paper about this subject. This is very technical, and also another one here again about leave one out cross validation. This was published at the Artificial Intelligence and Statistics Conference. Anyway, so a middle ground is five-fold cross-validation, where we shuffle the data, split it into 5 pieces, and then take each time leave one piece out, use the rest to train the model, and then test it on that left out piece. Okay, so when we want to do cross-validation for classification problems, we count the number of observations that do not match the true. So I here is an indicator function. we can, for example, here we are looking at the classification problem, two-dimensional data. The base decision boundary is purple dashed. Estimated decision boundary based on logistic regression will be a line, obviously, but if we use a quadratic, cubic, or quartic logistic regression, then we will have curved decision boundaries, and we see as the degrees increase, the decision boundary becomes more flexible, and for each of them we have the test errors of 0.2, 0.19, 0.16, 0.162, meaning that this has the lowest error, therefore it seems that degree 3 is the most appropriate. We can do the same thing for k nearest neighbors and plot the error rate in terms of 1 over k. Why? Because the larger the number of neighbors, the less complex the k nearest neighbor is. Let's see. Okay. So I will skip Bootstrap, but what I will do next is we will go over an R code to see what all of this that I said means in practice. Okay. So the data we will consider is the college data. So what is my data? So we have many colleges. We know whether they're private or public, and we have many information concerning the applications, number accepted, enrolled, top 10%, top 25%, etc. And so it's a classification problem. We want to predict whether the college, the university is private or not. So the number of rows will be the sample size. We have 777 observations. The number of features will be the number of columns minus 1. Why minus 1? Because one of the columns here is a response. So P is 17. Then all the my data minus the first column will be our X matrix, and the first column will be our response. We create a random order. So sample for so each time we call it, you get a different random order. Now we do it with n because we want to shuffle the data. Now we choose the number of folds. What do we want? We want a 10-fold, we want n-fold will leave one out. So n-fold CV is leave one out cross validation. Let's see tenfold. The next thing we're going to do is we're going to find the fold sizes. So we have n observations, and if we have 5 folds, then each fold size will contain n divided by 5 number of observations. And then we will round it down, and then we're going to say, okay, k nearest neighbors, I want to see what's the cross-validation error for the number of neighbors that goes from 1 to 10, and then from 11 to 100 in 10 increments. 1 to 10, so KNN values. Okay. Then for each of these values, we want to have an error. What is the associated error? What is the associated cross-validation error, essentially? And we create a matrix filled with zeros, because we will fill it with true values. And then we have logistic error, and then we have LDA and QDA. So we're going to try logistic regression and LDA and QDA for this problem. Okay. So we will have 2 for loops within each other. We will have 2 for loops within each other, and one will go over the folds. We have 10 folds, so it will go over the folds. And then the second one, for each fold, it will go over the number of flexibilities for the KNN. So over the KNN values. Okay? So the first thing we are going to do is we have created this random order, just shuffled indices, and then we are going to take the first fold, whatever it is. Maybe let's say this is the first fold. This J, first fold J is 1. 1 minus 1 is 0. 0 times fold size is 0. 0 plus 1 is 1. And then J is 1. So it goes from 1 to fold size. When J becomes 2, it takes the second piece. When J becomes 3, it takes the third piece, and so on and so forth. So these are the indexes of the data, indexes for each fold. We separate the validation part, response, and features, and the training part, response and features. Except that we are saying everything except whatever is that in false. Then we will use the KNN function, we will feed it the training data, and then we will also give it the validation, and then we say for the number of neighbors indicated at KNN values I, where there's the second for, give us the prediction for these validation responses, validation features. Then we compare the validation predictions for KNN with the true validation. We count how many mistakes was made. We add it to how many are already there from the previous folds, and then we just finish this loop. Now for logistic regression, we fit private against the rest of the features for the data indicated by everything except that is in the fold. Then we use the predict function, we give it the validation features, and we ask for a response. This will give us a probability between 0 and 1. We create a validation predictions filled with no's, and then if the probability is greater than 0.5 for all the points for which the probability is greater than 0.5, fill it with yes. The rest remain no. And then we compare the logistic error for validation, the true, with the predicted ones. We do the same thing with LDA. LDA, maybe this is the first time that we use it in this form. There is a function LDA, which is so simple to use. It's like the GLM. So you just indicate the response, the data, and then you have the fit. You feed the fit to the predict function, give it the validation, it gives you the prediction, and then you count. This prediction has many attributes. We want the class attribute. Essentially, we want to know what is the predicted label. We compare it with the true. The same thing goes for QDA. Okay, so let me repeat this again. We go over the folds, separate the validation part from the training part, then we feed the training part and obtain prediction for the validation, compare it with the true validation, and then we just sum up, add up the errors. Since we have n data points, we divide the errors by n, so we get an error rate. Then we say, okay, for which number of neighbors is the error the least? That gives us the optimal k, and yeah, that's it essentially. So let's run this. So what is the KNN? So error goes up, down, 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 and then it goes up again. This is for these neighbors. So which is the smallest? This will tell us. For a number of neighbors 9, we get the smallest error, which is this 0.604. Now, what about the logistic error? 0.65, slightly larger. What is LDA will be close to logistic, 0.64. QDA, 0.96. So you can see how they compare. Now this is 5-fold cross-validation. Now if we want 2-fold cross-validation, and is it print? Okay. Anyway. So I just run it, and it's this. This. You can run now n-fold cross-validation. Should take longer. You see, it takes longer. Okay, done. .65, QDA 0.99. Okay, so this is essentially how we can write the cross-validation code ourselves. In R, you typically don't need to. For most methods, there is a cross-validation that comes equipped with it, but not in all languages. So it is important that you at least have done it once and you know how to do it in case you need to do it.